All right, we're going to keep going with finding these zeros. I know it's getting a little exhausting here, but we have more zeros to find. All right, the next one, we're going to use the conjugate zeros theorem to find all the zeros of a polynomial. The conjugate zeros theorem says if a plus bi is a zero, so is a minus bi, which means if they give you one complex zero, you know another complex zero, and we can divide them out, okay, like we've been doing, but we can actually multiply together first before we divide to make fewer steps for us, okay? So let me show what that looks like. P of x is x cubed plus 8x squared plus 29x plus 52. And we know that that will have at most 3 zeros, okay? They tell us negative 2 plus 3i is a 0, okay? Which we know means that x minus negative 2 plus 3i is a factor. And we also know that that means that negative 2 minus 3i is also a 0, okay? Zeros, complex zeros come in pairs, okay? So that means that x minus negative 2 minus 3i is a factor, okay? So we know that our expression x cubed plus 8x squared plus 29x plus 52 can be written as x minus negative 2 plus 3i times x minus negative 2 minus 3i times another factor, okay? So what we can do, rather than trying to divide this by this, which is impossible, okay, we're going to divide it by both of these things at the same time, okay? So your x minus negative 2, okay, remember it's x minus negative 2, so plus 2 minus 3i, and then this would be x plus 2 plus 3i. We're going to multiply them together like we've done the past couple topics here, okay? And then we'll have x plus 2 plus 3i. So we'll have x squared, 2x, 3ix, 2x, 4, 6i, negative 3ix, negative 6i, and negative 9i squared. Remember, cancel, 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 cancel. Negative 9i squared is negative 9 times negative 1, so that's 9. Okay, so x cubed plus 8x squared plus 29x plus 52 is equal to x squared plus 4x plus 13 times this other factor. Okay, now I'm ready to divide. Okay, this is going to be a fun one. All right, we get to do some division here. So along one side, I don't know if I like this fat pen or not. X squared 4x 13. And our goal, I'm not going to rewrite it, but there's our goal. Okay, and remember, there will be no remainder. So if I get a remainder, I know I did something wrong. Okay, so first of all, I want to get x cubed. So then this is x. Right? I got my x cubed. And I'll have 4x squared. And I'll have 13x. Okay, I want 8x squared, so this must be 4x squared, which means this is 4, and this is 16x, and this is 52. And I've got my 29x and my 52 then. Okay, and everything worked out well. So this other factor is x plus 4. Okay, which means up here, this other factor was x plus 4, which means I found all my zeros, right? So if x plus 4 is a factor, x equals negative 4 is a 0. So I'm just going to use green to circle all the zeros. Okay, this one was given to me. This one I know because they come in pairs. And then this one I just found. So there's my 3 zeros for my third degree polynomial. Okay, all right, moving on. The next one, let's see, that was using the conjugate zeros theorem, right? Lost my spot here. Okay, the next one is linear factors theorem, and conjugate zeros theorem. Okay. So this one says, as an example, suppose r of x is a polynomial of degree 10. That's a lot. Okay. Also suppose our zeros are 4, -5, 7, and -5 plus 2i. Okay, now remember, this could have at most 10 zeros, but it doesn't have to have 10 zeros. In fact, an even function can have no zeros. An example of that would be a parabola that opens up, right? We know these quadratic functions with an x squared, and it could have up to 2 zeros, but they could have no zeros at all. But we also know that it won't have more than 2. So this one will have anywhere between 0 to 10 zeros, okay? So, and that's kind of what this was getting at us. Okay, so the first one, it says, find another 0. Okay, well, we can find that easily because zeros that are complex come in pairs. Okay, so since -5 plus 2i is a 0, -5 minus 2i is a 0. Okay. For part B, it asks what's the maximum number of zeros. That's the degree. Okay, so that's the degree is 10. Okay, and then for C, what's the maximum number of non-real zeros? Okay, well, remember the non-real zeros come in pairs. Okay, so, and we can have at most 10. Okay, and we know that we already have 4, -5, and 7, -5 plus 2i, and -5 minus 2i. So we have accounted for 5 of them. Okay, possible 5 more. Okay, that could be it. It could just be those 5, or we could have some more in there. Okay, if we have more and they're non-real, they come in pairs. Okay, so if we have 5 left, okay, think like if I have 5 shoes on the floor, I could have at most 2 pairs, right, and then a random one. Or it could be they're all just 5 individual shoes and none of them match. Okay, but I could have 2 pairs of non-real. So 2 pairs, a total of 4, and 1 real. Okay, that's the most non-real I could get out of that. And then don't forget the 2 that I already have. Okay, so I have 2 here and a possible 4 more, so 6. Okay, is my maximum number of non-real. All right, that's kind of a fun one. All right, moving on. Next topic is finding the intercepts, asymptotes, domain, and range from the graph of a rational function. Okay, so if you remember, me look ahead on this one a little bit. I'm going to get another one here. Just want to make sure I'm covering the topics that you need. Okay. So your rational functions will look two different ways. Okay. They will either, and they're, if you remember the hyperbolas that you did in Algebra 2, those are rational functions. So one rational function could look like this. That's the hyperbolas that you're used to. Okay. And another way that you might see rational functions is again with asymptotes. Okay, but they're both on the same direction, like that. Okay, so there's two types that you could find. Okay, and what they want you to do here is they want you to find, I'm going to make a list here. They want you to find vertical asymptotes, horizontal asymptotes, they want you to find x-intercepts. They want you to find y-intercepts. Okay, and then they want you to find domain. There's a lot going on here. And range. Okay, so we're going to do this for each of these. I'm going to make kind of a table here. Oof. I'm going to switch pens because I'm not liking this fat one. Okay. All right. So, I'm kind of running out of space there. So we're going to do kind of both of these at the same time. Okay, and I'm going to put some numbers on these graphs here. Oh. Okay. I have to do that later. Maybe that's why I'm all glitchy. Okay, let's say that this is at -1, -2, -1. I kind of hate to make them the same thing. Let's say that this scale is different, -2 and -4. Okay, and then over here, let's say this is at 3, 4, 5, and 1, 2, -3. Okay, we'll do our best here. Okay, so this one on the left, the vertical asymptotes are always going to be parallel to the y-axis. So vertical asymptotes are always going to be in x equals. Okay, so our vertical asymptote, and I'll use, is going to be right here. And on the green one, it's x equals -1. On the yellow one, it's going to be x equals 4. Okay, your horizontal asymptotes will always be y equals. So we're going to have, let's do blue, y equals. Okay, so on the green one, your horizontal asymptote is y equals -2. And on your yellow one, your horizontal asymptote is y equals -3. Okay, now we're going to look at your intercepts here. Okay, your x-intercept, so where do we hit the x-axis? Okay, this one is going to be at -2. And over here, where do we hit the x-axis? Well, we hit it twice, right? That one has 2 x-intercepts. So that one's going to be 3 and 5. Okay, and now our y-intercepts, where do we hit the y-axis? Well, this one is going to be -4. And this one is going to be -2. Okay, now your domain is going to be all of your x values, okay? And these domains are going to be weird because there's only going to be one x value you can't have, and that's where there's the vertical asymptote, okay? So for the green one, it's going to be all the x values except for -1. So we'll go -∞ to -1 and -1 to infinity, okay? And for the yellow one, it's just x can't equal 4. So negative infinity to 4 and 4 to infinity, okay? For the green one, the range is going to be similar. There's just one y value that we can't equal, and that's where the horizontal asymptote is at -2. So negative infinity to -2 and -2 to infinity. Okay, so again, we can't equal the y-intercept and we can't equal the x-intercept. Okay, now the range on the other one's a little bit different, okay, because we actually are only at the horizontal asymptote and higher when they're both pointing in the same direction. Or if they are pointing down, we'd be at the horizontal asymptote or lower, okay? So this one, we could start it at -3, but not equal -3, and go to infinity, okay? So that range is going to be a little bit different for problems like that, all right? Okay, next one. We have finding the asymptotes of a rational function constant over linear. Okay, so in other words, we're going to have a number over x plus or minus something. Okay, so we have f of x equals -4 over -x minus 5. Ooh, that's a lot of negatives. Okay. So for this one, your asymptote, your horizontal asymptote, asymptote. Okay, for all of these, I don't think they're gonna throw you off here at all on them. Okay, is going to be y equals 0. Okay, that's just it. For all of these, the horizontal asymptote will be y equals 0. Okay, I'm sure they'll get to some later where it's not. Okay, your vertical asymptote is whatever makes the denominator 0. So -x minus 5 equals 0. So -x equals 5. So x equals -5. That's it. Okay. So for all of these problems, that's what you're going to do. The horizontal asymptote will always be y equals 0. The vertical asymptote, just take the denominator, set it equal to 0, and solve. Okay. That's a pretty straightforward one. The next one is going to be kind of similar. We are going to be doing finding the asymptotes of a rational function linear over linear. Okay, so for these, you're going to have something like f of x equals 10x minus 11 and -4x plus 6. Okay, so this one's going to be a little bit different. Okay, your horizontal asymptote is not y equals 0. It's going to be y equals the ratio of the leading coefficients. Okay, but your vertical asymptote is still going to be what makes the denominator 0. Okay, so your leading coefficients are just the numbers by the x's. Okay, so your horizontal asymptote will be y equals 10 over -4. And we'll just reduce it. We can divide them both by 2, and we can actually put that negative out front is probably the best format for that. Okay, so we'd have y equals negative 5 over 2. Okay, and then for your vertical asymptote, the denominator is 0. Okay, so negative 4x plus 6 equals 0. So negative 4x equals negative 6. Oops, negative 6. So x is negative 6 over negative 4. So x is 3/2. Okay, and they'll have you graph these two. So they want you to do, if this is your plane, you're going to graph y equals negative 5/2. So that's like negative 2.5. Okay, negative 5/2. And x is 3.5, so that's positive 1.5. There you go. Okay. Next one. More asymptotes here. Okay, still rational function. But we're going to have quadratic numerator or denominator. Okay, so for this one, your example is f of x equals 11 over x squared plus 3x plus 2. Okay, now what we're going to do here is you need to factor the denominator. Okay, so 11 over x plus 2, x plus 1. Okay, your horizontal asymptotes. Okay, and I'm going to look and see quick if they give you other, let's see here, if it's always just going to be a constant or if they're going to give you other functions. Oh, they're going to give you other functions. Okay, so your horizontal asymptotes. So if the degree of the numerator is less than the degree of the denominator, which we saw in the constant over linear example, two up from this one, then it's going to be y equals 0. Okay, if they're equal, it's going to be the ratio of leading coefficients. Okay, if the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. Okay, so we already saw the first two. Again, the degree of the numerator is less than the degree of the denominator when we did constant over linear. They were equal when we did linear over linear. Okay, and vertical is still what makes the denominator 0. Okay, so for this one, the degree of the numerator is 0. The degree of the denominator is 2. So we're in that first case there where the degree of the numerator is less than the degree of the denominator. So horizontal will be y equals 0. Vertical, we look at that denominator and it would be 0 if x equals -2 or if x equals -1. Okay, so there's your answers there. Okay. We can do another example of that one too. Okay. The next one, g of x is negative 9x plus 1 over 2x squared minus 6x minus 8. Okay, so same thing. I'm going to try to factor the denominator. So we can get a 2 out of there. Get your GCF. So we'll have x minus 4, x plus 1. Okay, so our horizontal, since the degree of the numerator is 1, right? This is degree 1 because it's x to the first power. The degree of the denominator is 2. So the numerator has a smaller degree than the denominator, so it's y equals 0. And then your vertical, what will make that denominator 0 will be if x is 4 or x is 1. Okay. We'll get one more up here. We have f of x is x squared plus 2x minus 3 over negative x squared plus 4. Okay, horizontal, since the degrees are the same, the numerator is second degree and the denominator is second degree, ratio of those leading terms, so 1 over negative 1. So y equals 1 over negative 1, or y equals negative 1. Okay, vertical, whatever makes the denominator 0, so negative x squared plus 4 equals 0. So x squared equals 4. So that would be x equals 2 or negative 2. And there's your asymptotes. Okay. Let's see here. Next one. Okay. We have finding the asymptotes of a rational function quadratic over linear. Okay, now this is going to be kind of a weird one. Okay, so an example of this one, we have f of x is x squared plus 2x minus 1 over x plus 3. Okay, now we know that since the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. Okay, but there's what's called a slant asymptote. All right, so there is no horizontal. Vertical, again, the denominator would be 0. So that will be when x is negative 3. Okay, and then to find that slant asymptote, we do long division. Okay, so our slant, we're going to divide. So we're going to take x plus 3 into x squared plus 2x minus 1. And again, for slant, we divide and we just ignore the remainder. Okay, so we're going to have our x squared here, which means x and 3x, which means we need a negative x. So a negative 1, negative 3. We would have a remainder of 2, but we just ignore it. Okay, so your slant asymptote would be y equals x minus 1. Okay, again, you just do your long division and you ignore the remainder. All right, I would encourage you guys to graph these. You can't use a calculator when you do them, but graph them so you kind of understand what's going on here. What this is going to look like is you'll have that vertical asymptote at x equals negative 3. You'll have this slant asymptote y equals x minus 1, so y-intercept of negative 1 and a slope of 1. okay? And what this actual curve looks like, oops, okay, is kind of looks like this. Okay, so I would encourage you to get on Desmos or on your calculator and graph these. Graph this, and graph this. Okay, which you can do on Desmos, and take a look at those. All right, so you kind of get an idea, an intuition here for what's going on. All right, we got another one here. Actually, you know what? I think I'm going to stop here and start another video.